So today I will mainly present the work which has been done by two talented PhD students, Marion Gzelka, who is now in postdoc in Amsterdam in the group of Daniel Bonne, and Marceau Hainaut, who is agrégé préparateur at the École Normale Supérieure de Lyon. And I will discuss about slip of polymeric fluid, and I will introduce you this subject right now. The question I want to deal with today is a very old question, which is the question of lubrication. I think here, that's all those pictures we get of people trying to do lubrication. So that's maybe a worker or a slave which tried to displace a big block of stone, which is a sphinx, which is the same kind of picture that you have here. It is more than 2,000 years before Jesus Christ. And you see that since this time, people were aware that putting a liquid between two solids will help to displace the two solids. And the way it works is called what is called a lubrication flow, and it's mainly what I'm interested in. And of course, you can do that in real life, or you can do that in silico. Here you have this classical paper by Gao in 1995. And since this time, for many reasons, lubrication has been studied in detail. And to discuss what is precisely in lubrication flow, what is of interest for me, I will enter in the very basic lubrication for dummies, which is, no, it works. Okay, sorry. And the question I'm interested in is how do we solve the Navier-Stokes equation? So what you know about the Navier-Stokes equation is that it's a partial differential equation that you can solve easily. So here you have the classical form. And to solve this equation, you need the boundary condition. And the boundary conditions that you know, that you learned at school, is that you usually admit that the fluid velocity at the solid-liquid interface, if the solid is at rest, you assume that the fluid velocity close to the solid surface is equal to 0. And the assumption is basically that the molecules of liquid which are close to the solid surface, they adhere on the solid, and due to this adhesion of the solids, these liquid molecules to the solid surface, they don't move when you displace the liquid close to this solid surface. And indeed, it's not always true, and there has been a long story of efforts in order to understand why it is not true. And basically, it's not true because there are no basic principle which says that it should be like that. Nothing from thermodynamical point of view says that the fluid velocity close to the solid surface should be equal to 0. So the velocity is not equal to 0, and the way people usually define the slip length, they do not measure. There are several ways of defining that. You could of course define the slip velocity, which would be the velocity of the fluid close to the solid surface, but it's not what you usually define to quantify the slip, just because if you do not make the fluid move, the slip velocity will be equal to 0, which means that the slip velocity is not intrinsic of the solid-liquid interactions. And instead of that, what you usually define to characterize the slip is the slip length. And the slip length is the depth in the solid surface where you would extrapolate the velocity profile of the fluid close to the solid surface to 0. So no slip will mean that the slip length will be equal to 0, and any change regarding to this non-slip boundary condition will be of interest. So of course, if you want to measure this kind of slip length, there have been a lot of technical techniques that have been developed among the years. It's like that. So mainly the easiest technique, sorry for that. At the end, I will be okay with that. So maybe the easiest technique or the oldest technique will be, well, you take a capillary tube, you apply a difference of pressure between the entrance of the tube and the end of the tube, and you measure mainly the flow rate. And if you use the Poiseuille equations, then you can extract from the Poiseuille equation the ratio between what you would have without slip, which is the classical Poiseuille flow, or something different. So if there is a slip, the flow rate will be higher. And if you compare the flow rate with or without slip, you will be able to measure the slip length. Of course, doing that is not really easy, mainly due to the fact that the flow rate in the capillary tube strongly depends on the radius of the tube, and you have to know precisely the radius of the tube in order to measure precisely the slip length in this capillary tube as soon as the slip lengths are small. So another technique will be to directly probe the fluid velocity at the solid-liquid interface, and an interesting way of doing that is to use evanescent waves. So if you take a solid here which is transparent, if you shine light here with evanescent wave, the light will only penetrate in a fraction of microns, let's say tenths of nanometer inside of the liquid. And if you have some solid particles able to go in this illuminated region, you will be able to measure the fluid velocity very close to the surface. So this is a very precise technique, but it's not that direct just because of the fact that you are using tracers if you are doing that, and the tracers can affect the flow properties, or they can also adsorb on the surface, which makes this kind of measurement something tricky in some point. Another technique that has been used quite a lot is to use a flow rate. So it's kind of the same mechanically based technique than the one before, where you force the drainage of a liquid between two solid surfaces if you are able to precisely measure the distance between the two surfaces and measure the flow rate. So you can do that either in a surface force apparatus, which is a technique that I've performed during my PhD, or you can also use atomic force microscopy, which is a little bit trickier because it's difficult to precisely measure the distance between the two surfaces. But if you study the squeeze flow between these two surfaces, if you control precisely the force and the distance between the two surfaces, if you compare what you will have without slip and what you have in reality, you will be able to extract precisely a slip length. Maybe a more uncommon technique is to use the quartz crystal microbalance. It's a technique where basically what you have is a solid plate. Above this solid plate, you have the liquid, and you impose a small shear using piezoelectric effect, and this leads to, by doing that, you create a flow in the liquid, and if you measure the viscous damping due to this oscillation, and you know what you would have without slip and with slip, you are able to measure the slip length. So there are plenty of techniques. I will present you another technique a little bit later, the one I've been used. And based on these different techniques which allow to measure the slip lengths, people have obtained very nice results for simple liquids. So if you take a state-of-the-art measurement for the slip length of water on different surfaces, so this is for water on surfaces where you can control the wettability of water on this solid surface. By changing the wettability, mainly what you do is you control the affinity of water with regard to the solid surface. And what you see is that if you take water on hydrophilic surface where the contact angle is small, what you have is mainly a slip length which is almost nothing, 0 or a fraction of nanometer. And if you decrease the affinity of water regarding to the solid surface, that you see here by increasing the contact angle, you see that you can go from 0 nanometers to, let's say, 20 nanometers for contact angles of 110 degrees. And you can do that by doing experiments, or you can do that also in numerical simulation, where you see the same trend, which is the fact that, well, first of all, there is some slip of water on solid surface. Then you can control the slip by changing the affinity between the liquid and the solid surface. But something interesting here, if you compare the experimental data and the numerical data, is that they do not fit that well. I mean, here the maximum slip length that you have in experiments will be 20 nanometers for a contact angle of 110 degrees. And if you look at this numerical simulation for 110 degrees, the slip length will be 1 or 2 nanometers. So the trends are the same, but the absolute value of slip lengths by experiments or numerical simulation are not the same. And I mean, the reason for that is that it's difficult on the left, it's difficult on the right. I mean, doing a nice measurement of slip lengths with simple liquids in the nanometer range is kind of a nightmare because any pollutions, any small changes in the surface will strongly affect the slip lengths. And here, I mean, the way you have to describe precisely the interaction of the molecules and the surface is also tricky, which means that, well, there is still a lack of experiment and numerical simulation in order to have a clear idea of what fixes the slip lengths for liquids at solid interfaces. And you can say, well, we do not care that much. I mean, if it's really difficult to make the experiment, it means that it's an effect that we don't care at all. But if we look at what we are doing right now in experiments in our labs, we are doing more and more nanofluidics where we try to push a liquid in pores which are narrower and narrower, where the possibility of having nanometric slip lengths becomes important. Here you have some examples from Lideri's Bocquet group where they have studied the flow of water in carbon nanotube of boron nitride nanotubes. They measure slip lengths of, well, it's much more than what we have on flat surfaces. So slip lengths could be for carbon nanotubes of 200 nanometers. And they see also an effect of the curvature of the surface, which is that, well, for this kind of experiments where you want to deal with a flow in small systems, slip lengths can be important. And also, if you think in terms of ultrafiltration, where you want to put some water, as an example, in pores, in graphene layer, knowing how the friction will be affected by the molecular interactions of the molecules and the surface is also important. Well, with simple liquids, the conclusion is it's really hard, even though it's really important. And what I want to do is to shift from simple liquids where everything is complicated to something where it could be easier, which is polymers. So, sorry. I think that you more or less all know what is a polymer, but I just want to give you two ideas of the reason why it could be interesting to study slip with polymers. The first idea is, well, since polymers, you know, are long molecules where you repeat the same unit several times, you can have even like something like 1,000 or 1 million of monomers which are repeated like that. And due to that, you can describe a polymer as a random walk, where the average distance between the beginning of the chain and the end of the chain scales like the size of the monomer times the square root of the number of monomers in the chains. This idea shows you that if you take very long molecules where n is really large, the size of the molecules could be large. So polymers are large objects, which makes that maybe we can expect to have slips which will be of the orders of tens of nanometers instead of 1 or 2 nanometers, due to the fact that the intrinsic length scales of polymers it's much larger. Another important idea with polymer is that if you take one chain like that, there is a large number of chains of other chains in the same chains, which means that polymers are usually entangled, and the fact that polymers are usually entangled makes that the viscosity of polymers are really large compared to the viscosity of simple fluids. As an example, there is this theoretical prediction by De Gennes, which has been verified several times, where you can show that the viscosity of a polymer melt scales like the number of monomers in the chains to the power 3. Well, experimentally, it's not 3, it's 3.4, but let's say it's something like that. So you can really change the viscosity of polymers by changing the number of monomers in the chain. So that's something that will be also important in this study. Okay? So why is that interesting? So it's interesting because if we come back to the definition of the slip lengths that we have, so I told you before that for simple liquids, slip lengths will be maximum of 20 nanometers, which is a very small effect. If you go to polymers, what people have measured are slip lengths which range from, let's say, 1 nanometer, which is small again, but people have also measured slip lengths of 1 millimeter, which means that polymers, they can slip a lot. And since they can slip a lot, first of all, the deviation to the classical V equals 0 boundary condition is really important. So in practical situations like extrusion of polymers, you have this very strange shape of fibers of polymers which are extruded due to this kind of large slip lengths. And the second idea is that, well, if we deal with very long slip lengths, it could be much easier to measure this kind of slip lengths, and maybe we can learn some stuff from polymer slippage that will be difficult to learn from other fluids. Okay? So the first idea is why do polymers slip that much? And I think that we can come back to the history of the slippage of fluids to understand that, and mainly to Navier. So mainly if we come back to the definition of what is, where does the Navier-Stokes equation, basically the Navier-Stokes equation says that there is some dissipation in the viscous fluid due to the fact that different layers of fluids in the fluid, if they do not have the same velocity, there will be a friction in between the layers. So there will be a stress which will be proportional to the viscosity times the variation of velocity inside the fluid. So Navier already pointed out that we could make the same linear assumption at the solid-liquid interface, and he assumes that the stress exerted by a fluid at the solid-liquid interface will be a friction coefficient times a slip velocity. So again, it's the same of kind a linear hypothesis of linear response at the interface, where you assume that the stress is proportional to the difference in velocity, and so so Navier wrote that. So if you write these in the bulk and these at the interface, and you write the stress balance at the interface, I skip the math, but you will end up by is this equation where you will be able to say that the slip length B that we measure in experiment is simply the viscosity of the liquid eta divided by K, this friction coefficient at the interface. So this is really interesting because it tells us something which is the fact that the slip length is not something completely intrinsic of the slippage, basically because it's a comparison between the bulk properties, the viscosity, and an interfacial properties, which is this Navier coefficient. So based on that, Dejean proposed an explanation in order to understand why the slip length of polymer should be large. And Dejean's hypothesis was the following. He says that, well, basically, let's assume that we have a fluid of monomers like that. So the slip length will be the ratio of the viscosity of the fluid of monomer divided by this friction coefficient at the interface. So it's exactly the same hypothesis as the one I've written before. If I polymerize the fluid, which means that if I connect all the monomers in order to get a polymer from this fluid of monomers, what will that change? So it will change the viscosity, since we say that the viscosity of a polymer fluid increases a lot due to the fact that all the monomers are connected. And what Dejean said was to say, well, it will not change anything about the K friction coefficient at the interface. And the hypothesis, which is really strong, will be to say, since K is something which is really local at the solid-liquid interface, if we go to this fluid of monomer to this fluid of polymers, this K value doesn't change. And if we assume that this K value is the same for this fluid of polymers and this fluid of monomers, at the end, it will mean that the slip length for a fluid of polymer will be the slip length for a fluid of monomer, which should be small, as we have seen that for small molecules, the slip length is small, but it will be amplified by the ratio of the viscosity of this fluid of entangled polymers and this viscosity of fluid of polymers. So the idea of Dejean is the following. The polymers slip a lot simply due to the fact that they are more viscous. And then he also predicted that the slip length should increase like the number of monomers in the chain to the power 3. And does that work? Not that bad. So here you have some results by Oliver Bumschen in the group of Karin Jacobs in Saarbrücken. And they have measured the slip length with respect to the molecular weight, which is exactly the same as the number of monomers in the chain. And what they have in this log-log scale is that at least for large molecular weights, they observe that the slip length increases like the molecular weight to the power 3, as exactly predicted by Dejean's hypothesis. So it tells us that possibly it's possible to learn something about friction of simple fluids by using this trick of amplification due to the fact of this polymerization. So it's exactly what we have done in my group. And here I want to discuss the system we have mainly worked with. And we have mainly worked with polydimethyl siloxane as a polymer. So polydimethyl siloxane is a very nice polymer for physicists because it has a glass transition temperature which is really low, which means that when we are dealing with it at ambient temperature, we are far above this glass transition temperature. And it's also interesting because we can have it in two states. we can have it as a liquid, and it's mainly all the silicone oils or all the mineral oils that you use for your motor engines as lubricants. So that's very available polymers with different molecular mass, different lengths. And you can also cross-link it in order to make it not able to flow and to make an elastomer. It's what you use in a lot of prostheses or in microfluidic device. So here it's exactly the system that we were using, which is a very good model system. And we are dealing with this kind of system with different ideal surfaces where we try to avoid any adsorption or any strong interaction between the fluid and the solid. So how do we measure the slip length in our group? So the way we are measuring the slip length is, well, we are trying to work only with systems where the slip length is quite large, and the way we are doing that is that we are working with a mix of polymers like PDMS, as explained before, which are the classical one, and we add to this polymer some polymers of the same chemical nature, where we have added some photobleachable groups in order to make and fluorescent groups in order to make the polymer fluorescent. And the way we are doing that, so we put the liquid, the polymer fluid, which is now fluorescent, in between two plates, and if we shine light if we shine a line in this polymer fluid, which is really intense, using a laser, an intense laser, what we will be able to do is mainly to destruct the fluorescence on the line here. And now if we shear the upper plate, this line will be tilted like that, and the tilt will be a measure of the shear that has been applied during the displacement of the upper surface. And if there is some slip, at the bottom, here the bottom of these lines will slip due to the slip, and this allows to measure slip length here by simply seeing how this line is tilted and shifted during the shear. So by doing that, we are able to measure slip lengths between 10 micrometers to 2 millimeters. So very nice technique in order to measure the slip of polymer fluids. What is interesting here is that we do not use any tracer, so we do not change the flow by adding solid particles, and we can also measure the slip length with respect to the shear time in experiment. In order to do this experiment, we have to take care of some important experimental facts. First of all, the main trick is that this line shouldn't disappear during the experiment, so we have to be sure that the diffusion time of the polymer with respect to the experiment is long. So here, since we are using very long molecules, the diffusion times will be among a couple of hours, which means that this straight line doesn't disappear in this experiment. And unfortunately, in this experiment, we are not able to measure the stresses during the shear. So from this kind of experiment, what have we measured so far? First of all, here we have measured the slip length here of three polymers with different molecular weights, going from 600 kilogram per mole to 900, almost 1,000 kilogram per mole. And here you see that the fact that you change the molecular weight changes a lot the slip length, and it's exactly what has been predicted in the previous work by Dejean. Well, it's not, the slip length here with respect to the shear rate is not constant, and there is a small decrease of the slip length with respect to the shear rate, and it's mainly due to the fact that if we make some rheology of these polymers in the same kind of shear rates, between 0.1 to 10, let's say, we see that there is a beginning of shear thinning, which explains why there is here this small decrease of the slip length in this experiment. And by doing that, well, we are able to test the Dejean prediction, which is that we are able to test that the slip length with respect to the viscosity is something which is more or less linear. I wouldn't say that it's perfectly linear, but since we have only one decade, but here we see that mainly, as predicted by Dejean and Navier, we measure here with this kind of polymer flowing on short PDMS chains that the slip length is proportional to the viscosity. Well, so here we test this. B is proportional to eta. So can we say something about this K value? Because here what we want to say is that if we want to understand the friction of a liquid on a solid surface, we could be able to extract this value from molecular parameters or to connect this value to molecular parameters. So we have tried to do that by doing some other experiments. And what we have done as experiments is something completely different in terms of setup. Is we have measured the friction between a sphere here of PDMS. So that's the same kind of polymers, but now they are cross-links, which makes that they are not able to flow. That's an elastomer. So it's here we have an elastomer of PDMS. And here, so it's a solid, a soft solid, but it's a solid. And here we have studied how is the friction between this rubber here and the solid surface, which is exactly the same than the one before, which were small chains of PDMS. So we measure the friction force with respect to a PDMS, and we measure the contact area between this sphere of PDMS and this solid surface. And here you see. Well, you see a lot of dust, but even though you see that the contact is spherical, which means that we can monitor the contact area here between the two solid surfaces. Why is this contact area important? It's important just because, contrary to what we would have in solid friction, usually when you study friction between two hard surfaces, what you assume is that the friction force required to slide two solids over each other, you assume that this friction force will be independent on the contact area of the solids, and it is mainly due to the roughness of the solids. It is the classical Coulomb's law. And here, the important point is that since we are dealing with really soft solids, like PDM, I mean, not really soft, but soft solids, the Young modulus here is around 1 megapascal. And we are able to make really smooth surfaces. We have really an intimate contact between the rubber here and the solid surface, which makes that the force here is really proportional to the contact area, which means that here, if we want to describe the friction between this rubber of PDMS and this small carpet of PDMS, we do not have to use as a quantification of the friction coefficient, but instead of that, we have to measure the slope of this line, which is the shear stress between the two surfaces, which is the force divided by the contact area. And indeed, you know more or less that for soft solid like elastomer, the classical Coulomb's law are not valid. You know that from experiment because on your cars, if you have cars or you know what a car is, you know that the tires have not the same size than on a bike. And if you would assume the Coulomb's law, you would say that it's not important. The size of your tires are not important, but there are for elastomers where the friction coefficient strongly depends on the contact area due to this, the fact that the friction force between smooth surface is really proportional to the contact area. Well, if we measure the friction stress sigma with respect to the velocity here for this contact between a rubber of PDMS and a carpet of PDMS, first of all, we measure a straight line in the log-log scale, which means that with a slope of 1, which means that the stress is proportional to the velocity. And if the stress is proportional to the velocity, we can extract a friction coefficient of friction, which is of this order of magnitude as you see here. And now what we have done is, well, can we compare the friction coefficient here extracted by the friction of this rubber solid surface to the friction exerted by the same fluid, by the fluid of PDMS on the same solid? And here are the data. So for some experimental reasons, there are no overlap between the friction of fluid experiments, which are here, and the friction of solid PDMS, which are here. But you see that mainly everything is on the same master curves, which says that at the molecular levels, the mechanism of friction of an elastomer, which is here, and of a fluid, which is here, are exactly the same. Which is in a good agreement with the pictures proposed by Dejean that the friction should be really local. I mean, the only difference between the fluid of PDMS and an elastomer of PDMS is at large scale. It's at the size of the entanglement or the size of the crosslink. But at the molecular level, an elastomer of PDMS, it's mainly a liquid of monomers which moves. And it's explained why we have exactly the same friction here, both in elastomer and in fluid. And if we want to understand what is this value of this K friction coefficient that comes from the Navier law, we can come back to what it should be. Well, it should be something that we could be able to measure independently, simply due to the fact that here, mainly what we have done as experiment is experiment where we have studied the friction of PDMS flowing on a small carpet of PDMS, so it's mainly PDMS on PDMS here. And the friction of two monomers of PDMS, we know it from other experiments, completely other experiments, which are rheology experiments. If you want to measure the viscosity of a fluid of polymers like PDMS, if the molecules are not entangled, so you can use the Stokes-Einstein law and measure what will be the friction of a monomer just by studying either the viscosity or the diffusion coefficient, and you will be extract a value for this friction coefficient. And the prediction for the value of the friction K coefficient from rheology measurement is simply half of what you measure with respect to slips, which tells us that really we capture the main molecular mechanism in friction by just comparing these two kinds of experiments. So now, since we think that we have shown that really polymers are an easy fluid in order to understand what are the molecular mechanism of friction, the next question was, can we play on this K coefficient by changing the temperature? And indeed, we are looking at the literature before doing the work of Marceau-Hainaut and Marion Zelka. The data in the literature were a little bit scarce. If I look at this data here, so here it's the slip lengths you have different polymers with different molecular weights. Here they had a slip length of 7.5 micrometers, which was decreasing with respect to the increasing with respect to the temperature, but then decreasing. Here it was increasing. So in this kind of data, it was kind of a nightmare to know to understand what will be the effect of the temperature with respect to the slip. So there were more nicer data in the group of Karin Jacobs, where what they had was, well, it was polystyrene flowing on solid surfaces. So on some surfaces like Teflon, they measured mainly a slip length which was independent of the temperature, whereas with some other solid surfaces, they measured a slip length which was decreasing with respect to the temperature. So there seems to be kind of a discrepancy. So our first idea was it was not that easy to understand that, and maybe our first guess would have been to say, well, if we increase the temperature, we will make the movement of the molecule close to the surface easier. So our first guess will be that the slip length will decrease with respect to the temperature, which is exactly what they have here, which is okay. Well, but we have done some experiments, so we have used exactly the same technique where we have measured slip length B with respect to the viscosity for different temperatures. So sorry for the range of temperatures. The way that Marceau did the experiment is he was mainly changing the temperature in the room, so it is 3 points. And here he gave up at 40 degrees and he put the experiment in a box and he was not able to go up at temperature higher than 50 degrees. But what you see here in our experiment is that for this kind of polymers, mainly we measure something which is completely different from that has been measured in the group of Karin Jacobs, is that we measure that if we go from 20 degrees to 50 degrees, we measure an increase of the slip length. And the effect of the temperature, which is quite evident here, it's a little bit messier here if we change from a solid surface, which is a silicon wafer covered by OTS, to a silicon wafer covered by the same carpet of PDMS, where mainly we measure a small effect, again a small increase of the temperature, but really small. So our idea was, well, are we able to tell something about, can we use the same tricks that we have used before by comparing the effect of the temperature for the slippage of a fluid of polymers and the slippage of a fluid of elastomer? So we have done exactly the same. So the data are a little bit nicer here for classical trigonometry experiments. So here that's the stress with respect to the velocity. And here you see the fact that the stress decreases with respect to the temperature, which does not mean that which is not exactly the same that here we say that the slip length increases with respect to the temperature. Here we say that the stress decreases with respect to the temperature. Here we see almost no effect of the temperature with the stress, but in between, you have the viscosity because the slip length is the viscosity divided by this K coefficient. Here we measure directly the K coefficient, and here we measure the slip length. So what we have proposed indeed in this work was to say, well, we know that for the viscosity of a fluid, if we are far above the glass transition temperature, can be described by a simple Arrhenius law, which sees that the fact that if we increase the temperature, the viscosity of the fluid will decrease. So what we have tried to do is to say, well, let's assume that we will have something of the same, that we can write something exactly in the same spirit at the interface, which will say that the Navier coefficient, the Navier interfacial coefficient, will be a constant times an exponential of an activation energy for the solid-liquid friction divided by RT. So we have done that. So well, from this, so here it's K in a log scale with respect to the inverse of the temperature. So from that, of course, I wouldn't claim that we prove that we have an Arrhenius law, but I can from that extract an order of magnitude of this activation energy. And what I see here in this data is here we have the data for the solid friction experiment. The data for the fluid experiments, for PDMS sliding on PDMS, and here the same for PDMS on OTS. Here's the sliding experiment, and here is the fluid flow experiment. And from that, we can say that mainly, the activation energy that we measure both in the friction experiment and in the fluid experiment are the same, but they can differ regarding to the solid surface on which the liquid is flowing. So at the end, I think it's the interesting idea is the following here, is that if we want to understand why there are so many discrepancies in the effect of the temperature with regard to the slippage in the literature, we have to take into account the fact that we have two activation mechanisms which are in competition here at the interface. First of all, we can assume that we have this Arrhenius law for the solid-liquid friction coefficient. And we have also an Arrhenius law in order to describe the effect of the temperature to the viscosity with regard to the temperature. And if we combine the fact that B is equal of eta over K, then the slip length will scale like kind of an activation process where the activation energy is simply the difference between this activation energy and this activation energy, which means that this can be positive or negative regarding on the values here of the activation energy. So no, sorry. So for that, well, if we come back to what we had for the PDMS flowing of OTS, we have kind of the activation energy for the viscosity is really different from the activation energy for friction. And the activation energy that we measure for friction is higher than the activation energy that can be measured for viscosity, which means that here we understand why B decreases with T when we make some PDMS flowing over OTS. And what is interesting here is that we have also worked on PDMS liquid flowing over a short carpet of PDMS. And here, if the mechanism of friction are the same, what we should have is that the friction, the activation energy that we expect at the interface should be of the same order of magnitude or even of equal to the activation energy that we have at the interface. And within the error bars, it's really compatible. And here we measure almost the same activation energy for the viscosity and for the friction, which means that we more or less understand why B should be independent of B is independent of the temperature in our experiment of PDMS flowing of PDMS. So it's really due to the fact that here, since in the bulk it's PDMS monomers flowing on PDMS, and at the surface it's PDMS molecules flowing of PDMS, we expect to have exactly the same order of magnitude for this two activation energy, which gives this independency of B with respect to T. I think that a nice question will be what happens if we take some system close to the glass transition temperature. Indeed, if we go close to the glass transition temperature, what we should have will be a viscosity which shouldn't be able to be described by an Arrhenius law. We expect to have a divergence of the viscosity or a large increase of the viscosity when the temperature becomes closer to the glass transition temperature, if we take some laws like the WLF. And one of the questions is, if we go close to the glass transition temperature, will we be able to write some WLF-like laws for the friction values? And since now there are only a small number of values of the effect of the temperature on friction, which avoid to have a clear idea of what happens close to this TG. And of course, another way of, I mean, the divergence will be a little bit different, but knowing how the temperature will affect both K and eta close to a phase transition, not the glass transition, is also something that we would like to study in more details in the future. How much time do I have now?
Couple of minutes, but you can also close now.
Yeah, I mean, yeah. Because I have an extra paragraph that I can skip, so I will skip. I will go directly to the conclusion in order to have time for the discussion. So in that way, no. So I thought that at least at the end I would have learned how to work with it, but. Well, what we have done also was to study. Up to now, I have mainly studied I just tell you this result here. Up to now, what I have dealing with was the slippage in the continuous regime. But one of the questions was, how do we go from a situation where the fluid is at rest to a situation where we slide the two surfaces? And what we have measured so far was the fact that the slip length, when we go from no shear to a constant shear at a given velocity, was an increasing function of the shearing time, and that the characteristic time of increase of the slip when we go from the fluid at rest to a fluid continuously sheared is the reptation time of the polymeric fluid in this kind of experiment. So now I come to my conclusion. So I hope that I have convinced at least some of you that there is some interest in working with polymeric fluid in order to understand some molecular mechanism of friction. And the way is mainly that these are big molecules and there are viscous liquids which allow to go to higher slip lengths and make the experiments much easier to what we will have with simple liquids. And so far for for polymer melts, what I would like to emphasize are the following points. First of all, keep in mind that the slip length is not something intrinsic. It's really a combination of a bulk properties and an interfacial properties. So it would be more interesting to speak in terms of Navier friction coefficients than in terms of slip length if we want to really understand what happens in the experiment. Then regarding to that, the friction is a local mechanism, so it's completely independent of the degree of polymerization, which makes the polymer really useful in order to understand this molecular mechanism of friction. Of course, we can play with the temperature in order to understand the slip length. So finally, there is still a lot to do. I discussed already about the glass transition temperature. And of course, when we deal with polymers, the question of what will be the effect of the concentration if we deal with polymer solution is something interesting. And of course, polymers can be polyelectrolytes, so you can add some charge on these polymers, and you can play with both electrostatic interactions and the slip lengths. So that's still an open question that I would like to deal with in the future. So with that, I would really like to thank the two PhD students, Marion and Marceau. We have done all the experiment, and you see with my ability to work with a laser pointer how I'm bad with experiment now. I would like to thank Liliane Léger, with who I'm working on this question of slippage these years. Alexis Chenevière, who has been part of this project, and a lot of collaborators like Eric Druckenmüller, who has done all the chemistry, former collaboration with the group of Elisabeth Charlet in Lyon, and the ANR who funded this project. And with that, I thank you for your attention.
So maybe I missed something, but so at large concentration or even at strong shear, I would expect these polymer fluids to show some non-Newtonian behavior. So in particular, shear thinning, I guess.
Yes.
So how would it change?
Yeah. Up to now, we have never really worked. I mean, we worked just at the onset of shear thinning. My actual guess will be that it wouldn't change that much, which means that if I write B is equal to eta over K, I would say that, okay, if we go to shear thinning, eta will decrease with respect to the shear rate. And K, the question is now, is that possible to imagine that we have a kind of shear thinning effect in K? I would say that in most of the situations where we have really passive surface with no adsorption at the surface, we shouldn't have any effect like that on the K value, like shear thinning effect, mainly due to the fact that the shear thinning is really due to the alignment of the chains in the polymers, which is, it's a non-local effect. It's not at the monomeric scale. So my guess is that for very passive surface, K will be independent of the shear rate, and eta will depend on that. And of course, if there are some there are some data on that in the literature. If you graft some polymer chains at the interface, and then we can enter to non-Newtonian response of the interface. But usually, what we so far here in this very model system, we just try to avoid that.
But then eta, so if it's shear thinning, eta will decrease. So
yes.
B
will decrease. And no, sorry, yeah. Okay.
So do I understand correctly that if you define a slip length
yes.
B,
yes.
then the channel must be much larger than B?
Yes.
Surface must be much smaller than B.
Exactly. Which is the case here. I mean, I'm dealing with silicon wafer with a roughness which is nanometric, and the slip length I measure is micrometric to millimeters. So
but what would change now because if you have the slip length of millimeter, then you can, because the size of your polymer is much smaller than a millimeter, right?
Yes.
So you are very quickly in the regime where, for example, the size of your channel becomes smaller than the slip length. Yes,
there is. I mean, with this kind of experiment where there is a big. I mean, of course, the roughness affects the experiments. When the roughness becomes really large, the question is, where do we define the position of the solid with respect to, I mean, then there is a question of zero. Where is the zero of the solid surface with respect to the slip length? I mean, so there are some theoretical prediction of that. I mean, a fluid flowing on a rough surface with a big slip length. I mean, if I assume that B is not affected by the roughness, there are some theoretical prediction. But one of the question, I don't know if it's really your question, but I think that one of the experimental questions now is, what is the minimal roughness that we need in order to kill this slip? Because for simple liquids, the slip lengths are nanometric, and the molecules are nanometric, let's say. I mean, there is maybe one order of magnitude between the slip lengths and the molecules, what is interesting here with polymer is that there is a kind of decoupling between the length scales of the molecules and the length scale of the slip lengths, and that's one of the things I would like to study in details also.
So if you so in the end it depends all on. So in the end it depends all on the Navier coefficient. So
yeah.
Meaning that it depends really still on molecular interaction between the monomers and so meaning that. If you think of making a lubricating film on the surface, I mean, the monomer would slip much faster. So have you tried that, I mean, to coat your surface with some, I don't know, tiny amounts of fluids or using these impregnated surfaces, etc.? Because
yeah, I've never done that. I've mainly been sticking with a very simple interface, but yes, that's I mean, that's a nice way of asking the questions. The bad way of referees will say, well, since you are dealing with polymers, there is always some polydispersity in your sample. How can you be sure that you don't have a small layers of smallest chains at the interface that will act as lubricant? So, I mean...
Yeah, no, I would say it in a reverse way. I mean, since you measure the slip length, which is simply amplified by the viscosity, which you know perfectly, so you know molecular details by a macroscopic quantity. So.
Yeah, I've never done that to make multi-layers. On purpose multi-layers interfaces. No, here we are. I mean, we are just using monodisperse PDMS, so we change the viscosity by changing the molecular weight, which is a good way of keeping the interactions between the surface and the fluid constant. Because if we add some plasticizer in order to change the viscosity, there is always a question of segregation of this kind of molecules at the interface, which could act either as lubricants or which could make a nano roughness which can change the slip. So we try, that's kind of the interest of these techniques that we have, which is, maybe less precise than some other ones, but we avoid tracers or anything added in the sample. The only thing we add are these labeled PDMS chains that we take long enough in order to have only small end effects. So what we think is that they do not change anything by changing the concentration of these labeled polymer chains, but we don't add plasticizer, sorry.
And I also have a question. Can you actually get a negative slip length?
Yes. The negative slip length, you can have it if you have something which strongly adsorb at the surface. Like if you take adsorbing surfaces instead of repulsive surfaces like in these experiments, then what will happen is mainly the fact that some chains will be really adsorbed at the surface and attached at the surface, and then the flow will only be possible at the top of these adsorbed chains that you can see as a negative slip, as a negative slip length. In lubrication flows, that's something quite common to have these negative slip lengths.
Okay, I think we've asked all our questions, and let's thank Frédéric again for this very nice seminar.
Thanks.